Good afternoon, everyone. Welcome back. My name is James Davenport from the LMS Computer Science Committee, where in fact I'm the IMA representative, which just shows how interdisciplinary this subject is. I first got to know Aretha when she was a research student at Bath with my friend Rob Scheichel. She volunteered, or conceivably was volunteered by Rob, the way things happen, to tutor on my novel interdisciplinary course, Programming and Discrete Mathematics, to 260 first-year mathematics students. Her explanatory skills impressed me then, so it's very fitting that 10 years later she is explaining her subject to this interdisciplinary audience. Over to you, Aretha.
Okay, thank you very much for the nice introduction and for the invitation to speak here. So, let me see. Yeah, can you see the screen I'm sharing?
Yes, that's working.
Yep, and you can see my mouse as well. Yep, okay. So thank you very much. So what I wanted to talk about today was some of the recent work that I've done on Gaussian process regression. So the purpose of the talk is really just to kind of give everyone a flavor of how tools from applied mathematics and numerical analysis can kind of be used to get some insights into methodologies that maybe come from computer science or statistics, such as Gaussian process regression, and kind of give you some insights into how these methods work and what kind of theoretical properties they have. So even if you don't understand all of the technical details, I hope you can kind of see how there's a lot of tools from a lot of different areas coming together. So this is the outline of my talk. So I'm going to start with just giving you the problem formulation, so just explaining to you what problem I'm interested in solving, and then going to explain how you can do that using Gaussian process regression. And so that would be the way that we solve this problem that we're interested in. And then I'm going to talk about some of the properties of Gaussian process regression, so in particular how you can get some convergence estimates, or in particular as the amount of training data that you have goes to infinity, what you can say about the process. And then I'm going to be talking a bit about deep Gaussian process in the last part. So again, how you can use some tools from applied mathematics to kind of get some insight into these deep Gaussian process constructions and how they work. Okay. So let's get started with just the general problem formulation. So what I'm interested in is recovering some unknown function f. So I have some function f here that just maps from some domain u into the reals. And what I know about this function f is just this training data that I have here. So I have some function evaluations, so just some points un in the domain of f and the corresponding output values. Right? And then I want to use this observed data y to reconstruct or learn what the underlying function f is that is generating these outputs. Right. So that might seem like quite a simple problem to solve, but let me tell you that one, it's a problem that is very important in very many different applications. Right. So I'm sure those of you coming from computer science and machine learning have probably seen this problem many times, but so it does appear in machine learning very often, where you have some training data in the form of these input-output pairs, and then you want to maybe predict the output for a new input. So if you then want to predict f of u star for some new value u star, essentially that means that you want to learn what your function f is. Right? So it's a problem that is quite important in applications. And it's also not a problem that is actually very easy to solve, right? So in complete generality, if the function f can really be anything, this is quite a difficult problem to solve, right? So your f could be very complicated. It could, for example, be multi-scale, so it could involve many different length scales. It could be very high dimensional, so this domain of f could be very high dimensional. The f could have very steep gradients and all things like that, which make the function f quite complicated and quite difficult to learn. And so this is as I said, the problem that I'm interested in. The way I'm going to solve it is in a statistical framework, in particular a Bayesian statistical framework. What that gives me is a probability distribution on the unknown function f given the observed data y. And so this is a statistical method that doesn't just give you kind of one approximation or one reconstruction of your function f, but it is something that gives you a whole probability distribution on f given y. And so what that allows you to do is that you have some uncertainty quantification in this recovery as well. Right? So if this posterior measure, what it's called on f given y, if that is quite narrow and really concentrates on kind of a small set of functions, then you're quite sure about what your function f looks like. Whereas if this posterior measure is quite flat and has quite a high variance, then you're not really sure what your function f is. And so you have that information in this posterior measure as well. Okay. And as I said, one particular thing I'm going to be interested in is what happens as n tends to infinity. So intuitively, as you get more and more training data, you hope that you will be able to recover the function f more accurately. And in terms of this posterior measure, the probability measure on f given y that we have, that would mean that your mean goes to f, so it concentrates on the truth, so the right thing, and the variance would go to 0. Right? So as n tends to infinity, the amount of training data you have goes to infinity, you kind of get a Dirac measure, so just a very peaked measure just on the truth f. Right. So how does that work? So this Bayesian statistical framework, as I said, what we're going to do is Gaussian process regression. So this is a method that is very well known in machine learning and statistics. There's a seminal book by Rasmussen and Williams about Gaussian processes in machine learning. It is just a particular instance of the Bayesian framework. So just because it corresponds to one particular choice of the prior distribution, right? So what you do is you follow the standard setup that you have in Bayesian statistics. So you choose a prior distribution on your unknown function f. And so in this case, as I said, we're choosing a Gaussian process. A Gaussian process is really just a distribution on functions. So it is a Gaussian distribution on functions. I've given you the definition here, right? What that means that we're now modeling f as a Gaussian process is that at every point ui in the domain of f, the f of ui is now a Gaussian random variable, right? So it is a random function in the sense that the value that it takes at each point ui is random. In this case, the f of ui is a Gaussian random variable, and then the mean is given by the mean function. So here in the first argument, we have chosen a mean function, which in this case is 0. And then we have a covariance kernel here, so that takes the role kind of the covariance matrix. And this covariance kernel gives you the covariance between the function at two different points, ui and uj. Okay. If you think about it more visually, you have these two visualizations here. So you now have a random function, so you can draw sample paths or realizations of this random function. They would look something like this. So on the left-hand side here, we have different realizations of the Gaussian process f. And you can also think of it in terms of the mean and the standard deviation. So in this case, we've chosen the mean function to just be 0. And as I said, at each point, your function f is now a Gaussian random variable, in this case with mean 0 and with variance 1. And so what these sample paths look like is that you get something that stays close to the mean, and then it fluctuates around the mean with the size proportional to the standard deviation that we have here. Right? So in this case, we get something that stays close to 0 everywhere and then fluctuates around the mean. And as I said, it's just one way of choosing a prior distribution on the unknown function f. Right. Then you do the standard update that you do in Bayesian inference or Bayesian statistics. So to get the posterior distribution on your unknown function f, given the observed data y, what you do is you condition the prior on the observed data. So you just take the Gaussian process prior that you put on f and condition it on going through these points. So the nice thing about Gaussian process regression is that you can actually do this completely analytically. So the posterior distribution in this case is known, and you can write it down explicitly. So it is again a Gaussian process, and the Gaussian process has a specific mean and covariance function that you can again write down explicitly. So I've given you the formulas here, but what exactly these formulas is not really important for this talk. It's just that you do know explicitly what this conditioned distribution is. So in particular, you then get an updated mean and covariance function. Right, so you update your mean to go through the observed points. So in this case, the black dots that I have here are the points that I have observed. So I'm conditioning to go through there, and you can see that the mean goes through these points, and then you also get an updated standard deviation. And at the points where you have observed your function, the standard deviation is actually 0, right? Because there's no uncertainty in the points there. You know what your function f is at those points, and so there's 0 variance there, right? Because you're always conditioning on going through those points. Similarly, you then get updated sample paths. So again, because you're conditioning on going through the observed points, all of the sample paths will go through those observed points. And then in between, they follow this Gaussian process that we have here. Right. So that is all that Gaussian process regression is. So you just put a prior distribution on your unknown function, and then you condition it on observed data to get the posterior. So as with all Bayesian procedures, you do have to think about how you choose your prior distribution, right? So that is something that typically depends very much on the application, and you need to kind of choose your prior distribution in a sensible way, right? So in particular, in this case, what you would want to do is to choose the prior to kind of be a good choice for your function f. So phrase that here as kind of reflecting properties of f. So what do I mean by that? So I mean the following. So the way that you choose your covariance kernel k is going to determine a lot of different properties of the sample paths of your Gaussian process. Yeah. So I've given you some examples here. So each of these 4 graphs shows you sample paths, 5 different sample paths from a different Gaussian process. So each of these graphs shows samples from a different Gaussian process, and you can already see that those sample paths look very different. Okay. So one thing that you can control is what I call the smoothness. This is known as the differentiability, or by smoothness, I mean differentiability. So how many derivatives the sample paths are going to have. So in the first row here, I've chosen a covariance kernel K, which gives you sample paths that are continuous but not differentiable. And so that's the exponential covariance kernel. For those who know what that is the covariance kernel of the Ornstein-Uhlenbeck process. And you can see that they do look quite rough. And in the second row, I've chosen a covariance kernel K, which gives you sample paths that are C infinity, so infinitely many times differentiable. So that comes from the Gaussian covariance, also known as the squared exponential or the RBF covariance. And so that's something that gives you very smooth functions. You can also control the contrast. This is just the marginal variance, so the variance that you have at each point in the domain. So it's just the kind of range of, or the amplitude of the fluctuations that you get. So whether for these sample paths, you go between -4 and 4, or you kind of go between -40 and 40. It's just the size of the amplitude. Okay. There's another important quantity, which is kind of the length scale of fluctuations. So this is really the correlation length scale that you have. And this is, it's the correlation length scale, and it's kind of the typical length scale that you see in your samples, right? So in these plots here on the left-hand side, I've chosen a quite large correlation length. So the lambda here is the correlation length. It's quite large. On the right-hand side, the correlation length is much smaller, and you can see that you get much more fine-scale oscillations in the sample paths, right? So here, the samples only vary very smoothly, whereas here you do get oscillations on a much finer scale, right? So all of these things, all of these properties of the Gaussian process and the sample paths are determined by the covariance kernel. Right? And in particular, there's typically some hyperparameters theta that govern all of these things, right? So there's typically some parameter lambda, usually, that governs this length scale. Then there's the sigma squared, the marginal variance. And there's typically also a parameter that gives you the smoothness. So all of these things are kind of tuned by hyperparameters in the covariance kernel, and you need to be able to choose them well if you want this method to work well, right? So you can imagine if you use a prior that gives you sample paths like this, but your true function really looks something like this, then that might not really work very well, right? So if you want this method to work well, you would have to be able to choose these theta in a good way, but the problem is that you don't really know how to choose them, right? So the only thing that you know about your unknown function f is in these observed data points y, right? So you only have the function values of f at a couple of points, and that's all you know about f. And so properties like this, whether it's smooth or whether it's highly oscillatory, is something that you just don't really know. Okay? So you kind of have to adapt the methodology to take that into account. So one thing you can do is kind of a full Bayesian approach, so this hierarchical Bayesian approach. So what you do in that case, you find a joint posterior of the unknown function f and the unknown hyperparameters theta in the covariance kernel. And then you just get the posterior that you're interested in as the marginal distribution of this joint posterior. So that would involve integrating out the theta, and that is something that is typically not possible. And so integrating out the theta, it's usually not possible to do analytically, and even numerically, it's just too expensive to do. Right. So what people usually do is empirical Bayes, or a popular option is empirical Bayes, where you compute an estimate of the hyperparameters from your data. So you use your observed data points to compute an estimate of the hyperparameters, so an estimate for what you think the typical length scale is, for example. And then you just use that and you kind of cheat a little bit and treat this estimate as the true value for the hyperparameters. So then you just take this estimated value, plug that into your prior distribution, and then do the standard prior to posterior update in the Gaussian process. Right? So that's why it's called the plug-in approach, that you just take this value that you computed for the hyperparameters and then just plug that in to your equations as though that was the true value. So exactly how you can compute the estimate of these hyperparameters is a different question, and also a very important question that is still it's quite difficult to do in some cases, and also very time consuming. But in this case, that is not the focus of the talk, so you can do that in however way you want. And what we're really focused on is kind of this posterior consistency that I was talking about in the beginning. So what happens as n tends to infinity, and in particular, does the fact that we have to estimate these hyperparameters, does that kind of influence whether we're able to recover the true function f as n tends to infinity or not? Okay. So this question of what happens as n tends to infinity and whether you're able to recover the true function f is, of course, something that people have looked at earlier. So there's some seminal work here. Of course, since then, there's been very many other people working in this area. However, in the particular setting that we're interested in, these results don't really apply. So there's a couple of particular things, but the main challenge is really that your estimated hyperparameters change with n usually, right? So if you're estimating them from the data, as you have more data, you would include that data in your estimates, and so these estimated hyperparameters really change with n, and that's something that most of the previous literature cannot really deal with. Right? So what we're going to do is we're actually going to use results that come more from an approximation theory or numerical analysis literature. So in that setting, you can deal with all of these things that, so you can deal with this particular setting that we're interested here. And so you can transfer a lot of results from, as I said, approximation theory and numerical analysis into this setting where you're interested in Gaussian process regression. Right? So just as a brief recap, what we wanted to do is we want to look at what happens as the number of training points n tends to infinity. And what we wanted to show is that the kn, so the variance of Gaussian process regression, goes to 0. So this is the variance of our posterior on f given y. And then the mean of the posterior, so the mean of f given y, tends to the true function f. Okay. So to show that, you can study the particular form of the mean. So the mean of the posterior is what is called a kernel interpolant. What does that mean? So one thing is it is an interpolant of f. Right? So that is because we're conditioning on these points. So at the points un, where we have observed our data points, right? So if we go back to the pictures, because we're conditioning on going through those points, we know that the mean always goes through those points as well. And so you have an interpolant in that setting. And then the kernel just means here that you're using the kernel as the basis functions. Right? So from the explicit expression that you have for the mean, you get this expression here. And so the covariance kernel k that we had in the prior, actually in this setting, kind of takes the role of the basis functions. Okay. So because you know that, because then you know that the mean is just a kernel interpolant of f, you can then use the results from the numerical analysis literature. And because the kernel k in this case takes the role of the basis functions in the interpolation, the type of results you get depend very much on the choice of k that you have made. Okay. So what I'm going to do now is just show you one particular result for a family of covariances that is very often used. So these are these Matern covariances. So this is a parametric family of covariance functions which has 3 hyperparameters. So theta, the hyperparameters theta, in this case the sigma squared, the lambda, and the nu. So the sigma squared is just the marginal variance. So that was the contrast parameter that I was talking about. So the kind of amplitude of the fluctuations of the function. And then we have this correlation length scale lambda, which was the typical length scale. So if lambda is very large, then you kind of just get long variations, whereas if the lambda is very small, then you get very oscillatory functions. So the last parameter is this nu, which is the smoothness. So it's related to how many derivatives your sample paths have. So the general formula for this looks quite complicated. So you have the gamma function here, and this is the modified Bessel function of the second kind, but it does simplify in some cases as well. So for example, if you plug in nu equals 1/2, then you get the exponential covariance kernel into the Arnstein-Uhlenbeck kernel. And as nu tends to infinity, you recover the Gaussian kernel, so the squared exponential kernel. Okay. So I'm not going to have too much time to talk through all of this. So I know it probably looks horrible and it has a lot of technical details, but this is just to show you kind of the types of results that you can get and that tell you something about what happens as n tends to infinity, right? So in this case, we now have our true function f, and here we have the mean of the posterior with the estimated hyperparameters. So this is something that tells you that the mean of the posterior tends to the truth. And then this result here is a result on the variance or the standard deviation, because the square root here. And it's the result that tells you that the variance of the posterior will go to 0 as n tends to infinity. The way we're measuring the errors are in the L2 norm. So this is an average error over the whole domain of f. The things that appear on the right-hand side are typical things that appear in approximation theory, and I think they're also known in the statistics literature. So for example, the h here is known as the fill distance, It's also known as the separation radius or the maximum distance. So in statistics, it's usually referred to as the maximum distance. And it's just a way of measuring how space filling your design is, right? So you look at all of your design points or training points, UN, and then you look at how far any point U in the domain of F can be away from any training point UN, right? So if this fill distance is small, that means that you have training points everywhere in the domain of F. And in particular, if you want this to go to 0, then you need a space filling design, right? So that is typically the thing that would then give you convergence as n tends to infinity. There is this other thing coming in here, which is related to some stability issues. But I don't want to spend too much on that because I'm realizing I'm already running a bit behind time. Yeah, so this is really related to stability. And so this is actually a term that is not decreasing in n, so it's either a constant or increasing in n, and so that can come in as well. Right. So as I said, I know it's a lot to take in, so let me just briefly recap the main points. So we don't need very strong assumptions on f. So this does work for any f that is in this Sobolev space. So if you're not familiar with Sobolev spaces, what this means is that the function f has mu plus d/2 derivatives that are square integrable. So this is an assumption on how many derivatives your function f has. The more derivatives f has, the faster you converge, and the smoother the problem is. And so the rate that you get depends on your smoothness mu. For the estimated hyperparameters, we don't require very strong assumptions. So if you want this precise result that you have here, all that you need to know is that they are uniformly bounded away from 0 and infinity. You can relax that assumption as well if you, for example, know that some of these estimates do tend to 0 as n tends to infinity. You don't need convergence, so that is quite often something where you have problems with identifiability of the parameters. That is not an issue, so we're not assuming that any of the parameters need to be identifiable or that the estimates that you have converge to anything. None of that is required. In some cases, you can get the optimal rates. So these are optimal rates for functions f in this particular class. And the final comment with this stability result that we had here, so this term with the mesh ratio rho, that really only comes in if you are overestimating the smoothness, right? So the nu star here is kind of the limit as your the limit of your estimated smoothness. Right? So the way to think about that is really that if your nu star is greater than nu, that means that you're choosing a prior distribution that is smoother than your function f really is. Right? So in that case, you're choosing a prior that is too smooth, and then you have some possible stability issues coming in. Right. As I know this is quite technical, so if you do want more of the details, I encourage you to look at the paper, but I hope that kind of gives you a flavor of kind of how some results from approximation theory can be translated into this context to give you some insight into what kind of behavior you can expect as n tends to infinity. Right. So this is just a quick summary of this part. So we looked at the Gaussian process regression, in particular, what happens as n tends to infinity. And the conclusion that I want you to take away from this is really that it does work in most cases, right? So this posterior consistency, so that as n tends to infinity, you recover the truth that is guaranteed under very mild assumptions. And if you do need to learn the hyperparameters, that is usually not an issue. So whatever hyperparameters you choose and however you estimate them, most of the time you still get convergence to the truth, right? So you might not get convergence at the optimal rates, but eventually as n tends to infinity, you will always tend to the right thing and recover the truth. Right. So for the second part of the talk, as I said, what I wanted to talk about was a bit about deep Gaussian processes, right? So that's a bit of a hot topic at the moment, is deep learning methods. So I just wanted to talk a little bit about our work on deep Gaussian processes. And so the deep Gaussian processes, you can use them again in the context of regression. So this regression problem that I talked about in the first part, you can, instead of using a standard Gaussian process as the prior distribution, you can now use a deep Gaussian process. Okay? So you would then do exactly the same as you had before. That you just put a deep Gaussian process prior on your unknown function f, and then you condition on the observed data y. Okay? So to do that, let's first look at what a deep Gaussian process actually is. Right? So similar to neural networks or deep neural networks, a deep Gaussian process has different layers. Okay? And particularly, we're going to denote by fl-1 a deep Gaussian process with capital L layers. That's just because we start numbering the layers at 0. Okay? And how do the different layers work? Well, they work in this way, right? So you have a hierarchy of Gaussian processes. The F0 is a standard Gaussian process with some covariance kernel. So this could, for example, be the Matern covariance kernel that I showed you just now. And then for the other members of the hierarchies of the layers higher up, we define these Gaussian processes conditionally. So the FL+1 given FL will be a Gaussian process where the covariance of that process now depends on the previous layer FL. Okay? So it's just a sequence of Gaussian processes, and they're all related, and they're particularly related in this way, right? So you'd have a Gaussian process F0, and then you can define F1 given F0 by using F0 to define the covariance structure of F1 and so on, and then you just keep iterating. I know this sounds very abstract at the moment, and it's probably not very clear how exactly this FL goes into the covariance structure. There's very many different ways that you can do that, so I'll show you 2 examples in the next couple of slides, exactly how to do that. So the nice thing about this framework is that it does, as I said, allow for a very large variety of constructions, so you can get very different types of constructions out there, and it is usually quite a flexible model that can model quite complex behavior. Right? So if you, for example, have a standard Gaussian process and you use something like the Matern covariance function, Matern covariance functions are stationary, so that would give you stationary Gaussian processes, so Gaussian processes that behave the same everywhere in the domain. Whereas these deep Gaussian processes, for example, can very easily give you non-stationary behavior, so behavior that is very different in different parts of the domain. Right. So one question that you can ask yourself is, how many layers do I really need? Right, so that's a question that you also always ask yourself with deep neural networks. And again, what you see in practice is that you don't really need very many layers. Right? So theoretically, you could include as many layers as you want, but in practice, you see that it's typically only a quite small number of layers that you actually need. So I'll get back to that in the end as well. So you can actually use, again, some tools from applied mathematics and probability theory to kind of give a justification for why, in this case, you only need a small number of layers. Right? And as I said, I'll come back to that later on, but first I just wanted to make sure that we kind of know what these Gaussian processes are and how they work. Right. So as I said, the way that the FL can enter the case, so exactly how you define this covariance structure of FL+1 given FL, you can do that in many different ways. Right. So one example is kind of the canonical construction for deep Gaussian processes, so the one that was done in this first paper on deep Gaussian processes. And that structure is very similar to the structure of deep neural networks, right? So in deep neural networks, remember what you do is you use the output of one layer as the input to the next layer. And that is exactly what you do here as well, right? So what you're doing is you're using the output of FL as an input to FL+1. Right? So what that means mathematically, you can write it down like this. Right, so you then have some covariance kernel that you evaluate at FL of u and FL of u prime. Right? Because if you think about it, if you usually would have your covariance kernel K evaluated at the points u and u prime, we now don't want to use the u as an input to F, but the FL of u, right? So we use the output of FL as the input to FL plus 1. Right. That, of course, only works if the output and input space are the same. So if the output space of FL is equal to the input space of FL plus 1. If that's not the case, then you just have to include another map. So if your FL goes from some U into R, then you need to define a suitable G that takes you from R back into U so that you can define this. And in that case, you just need to match and have a mapping from the output space of FL to the input space of FL plus 1. Yeah. This is really just composition. So you're composing the functions FL and FL plus 1. And as I said, it's very similar to the structure for deep neural networks, where you're using the output of layer L as the input to layer L plus 1. Yeah. So another example is based on non-stationary covariance kernels. And so this is a construction that was introduced by Paciorek and Shervish in this paper here. Yeah. So some of you might have seen it before. So as I said, it's a construction that is based on non-stationary covariance kernels. Yeah. So what you need for it is two ingredients. So you need one stationary covariance kernel, right? So as I said, so a stationary covariance kernel is just a covariance kernel of a stationary Gaussian process, right? So in particular, the covariance kernel will just depend on your two arguments, u and u prime, through the distance, right? So this will give you a Gaussian process whose behavior is the same everywhere in the domain. Okay. So the examples that I showed you earlier, these were all examples of stationary Gaussian processes, right? So if you look at what your function is doing over here and what it's doing over here, it looks exactly the same, right? So there's no difference in behavior between different parts of the domain. The second thing that you need is then a function which we're calling lambda of u, right? So this is actually now a non-stationary version of the parameter lambda that we saw earlier, right? So in this Matern covariance kernel and in the graphs that I just showed you, we had this parameter lambda, which was the correlation length scale parameter. If you have a large lambda, you get very smooth functions. If you have a small lambda, you get very oscillatory functions, right? So what you can do now is you can actually make this correlation length lambda dependent on where you are in the domain, right? So in some parts of the domain, you're then going to have small correlation lengths, and in other parts, you're going to have large correlation lengths. Okay? And then in this paper here, what they do is they give you a general recipe to make a non-stationary version of any stationary covariance kernel. And so once you have your stationary covariance kernel, you can make it into a non-stationary version just with this general recipe here. And so the lambda function is now the one that gives you the correlation. Right. So in the context of deep Gaussian processes, we're going to be choosing the correlation length lambda as a function of the previous layer, right? So that is now exactly how the previous layer FL is going to enter into the covariance structure of FL plus 1, right? So essentially we're using FL to define hyperparameters in the covariance structure of FL plus 1. And here in particular, we're using it to define the length scale function lambda. So because the lambda is something that's physically always positive, we do have to apply some transformation to the FL, right? So the FL is a Gaussian process, so in general it can be positive and negative. And so you have to just apply some transformation, capital F here, that transforms it into something that's always positive. Yeah. That might have been a bit too technical, so let me show you some pictures of what is going on. Yeah. So these are now independent samples of deep Gaussian processes and the different layers in the Gaussian process. So each column is an independent sample, right? And each row corresponds to one of the layers in the deep Gaussian process. So the first row is all of the F0s, the second row is all of the F1s, and so on. So we've got F2, F4, F5, probably missed 0, 1, 2, 3, 4, 5, 6. Right? So these are all the different layers, and you can see that the kind of behaviors that you get are very non-stationary in terms of the covariance length scale. Right? So in terms of the correlation length scale, in terms of the size of the fluctuations. Right? So here, for example, you can see that you have something here that is very smooth, right? So it doesn't really vary at all in this part of the domain, whereas you have other parts of the domain where you really get very fine scale features, right? So that's kind of the kind of behavior that you get with this construction that I showed you in this construction of deep Gaussian processes, where you use the layer FL to define a correlation length scale for FL plus 1. Okay. So that's the kind of things that you see. So these are the kind of processes that these deep Gaussian processes are. Okay. So as I said, you can use them as prior distributions in Gaussian process regression. Right? So we now want to apply the Gaussian process regression that I explained in the beginning, in particular to this function here. Right? So we here have this function that's almost a step function. It's not quite a step function, so it is continuous, but it does have very steep gradients in this part here. Right? So if you're using a standard Gaussian process, in particular a stationary Gaussian process, that is something that would be very difficult for it to do, because you have very different length scales in the domain, right? So you have these three parts here, here, and here, where the length scale is very large, right? Because the length scale is very large, but then you do have these two parts here where you would need this very small length scale to be able to capture that steep gradient and the big jump. Right. And we'll see that with deep Gaussian processes, that does work a lot better. So in particular, in this regression problem, we're going to have noisy point evaluations at 50 points. So we just have 50 points that are equally spaced on 0, 1 here. And then from that, we want to recover the function f. Right. So these are the results that we get. So what we've done is we've implemented an MCMC method, so a Markov chain Monte Carlo method, in particular Metropolis Hastings method. So this is just a method, an algorithm that allows you to sample from the posterior distribution. Yeah. So with deep Gaussian process regression, you no longer have the nice property that you're actually able to write down the posterior distribution analytically, right? So I told you for Gaussian process regression, you can write down explicitly what the posterior is. For deep Gaussian process regression, you can't write down the conditional distribution of f given y analytically, and so you have to use something like MCMC. Okay. So these are the results that we get. So on the left-hand side here, these are our final reconstructions for f. Right? And you can see they all kind of look like the function f that we want to reconstruct. This one here is the one using just a standard Gaussian process. Right? So in a way, it's just using f0. So this is just a standard Gaussian process. This is a deep Gaussian process with 2 layers. So we have this one hidden layer here. This is a deep Gaussian process with 3 layers. So we have the 2 hidden layers. And this is a deep Gaussian process with 4 layers. So again, you would have the 3 hidden layers here. Okay. And you can see visually that you are able to capture those steep gradients a lot better with the deep Gaussian processes. Okay. And also this next column that you have here, right? So that would always be the FL minus 1, if this is FL. And so this is supposed to represent the length scale of this function. In this case, the way we've implemented it, this is the inverse length scale. And you can see that you have a very large inverse length scale, so a small length scale at the points where you do have these jumps. Yeah. So it does work quite well. We can also do an example in 2 dimensions. So we now have this function that we want to reconstruct. And again, we're given the point values of this at some points in the domain. So this is just the contour plot of this function here. Right? So it's just a combination of different sines and cosines. And again, you can see that in this function, you do have very different length scales. So you have quite smooth parts here, and then you have very oscillatory parts here. Right? And again, the deep Gaussian process is able to capture that quite well. So these are exactly the same kind of plots that I showed you for the 1D function. So these are the final reconstructions that we have for f in the contour plot. So we want it to look something like this. And again, this is a standard GP. This is a deep GP with 2 layers, and then this is a deep GP with the 3 layers. Right? And you can see already visually again that the deep Gaussian process with 3 layers is actually able to capture this a lot better, and particularly these fine scale features that you have here is something that you cannot capture at all with the standard Gaussian process. You can also compute the error. So instead of just kind of inspecting it visually, you can compute the errors. So you have your true function f, which was the one that I showed you in the beginning. And then you can look at the means that come out from the MCMC. So this would be the ones that we see here, just the means coming out from the MCMC simulation. And then you can see, you can look at the L2 errors, so an average error over the whole domain with 1, 2, and 3 layers. And you can see that you do get substantial improved accuracy. So this was for the case of 1,000 observations that I showed you earlier. If you don't have as many observations, if you only have 256 data points, then you actually see that by increasing the number of layers, you actually start to increase the error again. So this is really just a manifestation of overfitting, where you then don't have enough data to really inform all of the layers. So the deep Gaussian process model kind of becomes too complicated or too complex, and you don't have enough data to inform all of the layers. So it is again the usual problem of overfitting. Right. But as I said in the beginning, in practice, you see that you can get away with a very small number of layers. So typically like 3, 5, or 10 layers is maybe all you need. You don't really need to go much higher than that. So if you want to say something about that mathematically and kind of have a mathematical justification for why you don't need very many layers, one thing you can do is you can use some results from applied probability. Okay? So in particular, the way that we've constructed our deep Gaussian process and this sequence of processes FL, right? So if we remember back to how we constructed this in the beginning, right? You start with F0, then you construct F1 given F0, then F2 given F1, and so on. So that construction naturally gives you a Markov chain. Okay? So a Markov chain is just a stochastic process with exactly that kind of covariance structure, that the current iterate kind of only depends on the previous one. Right? So the FL plus 1 only depends on the FL. It does not depend on FL minus 1 or FL minus 2 or anything like that. It just depends on the previous one. Right? So that then gives you a Markov chain. And so you can actually think about this process as a Markov chain, and you can think of it in terms of the ergodicity of that Markov chain. Okay? So if you can show that this Markov chain is ergodic, what that means is that it has an invariant distribution or a stationary distribution. And so as L tends to infinity, and for large L, you will actually have something that converges. So the FL, in this case, converges as L tends to infinity to this invariant distribution. And so in particular, in that sense, it has a finite depth, which is given by the mixing time. So the mixing time is just the time that it takes you to reach the invariant distribution. Right? I realize, yeah, I have maybe a couple of more minutes. So what I wanted to show you is just then a final result that tells you something about the convergence in L, right? So this result actually shows you that as L tends to infinity, so if you increase more and more layers, the deep Gaussian processes converge to something, right? So in particular, that means that at some point, increasing the number of layers and adding another layer is not really going to change your distribution or your model very much, right? Because it converges to something. And so you're going to be just very close to the limit that you're converging to. So let me just show you the result here. So again, I know it's maybe a bit too technical, but really what I want you to take away from this is that you can construct these deep Gaussian processes, in particular if constructed with this non-stationary covariance function approach that I showed you, that's based on the Pachurik and Shervish paper. Under very mild assumptions, you can then show that your chain does converge. So you can show that there is some stationary or invariant, so there's some invariant measure pi. We don't know exactly what it is, but there is some stationary measure pi such that the deep Gaussian process with L layers, right? So that's what this is, the deep Gaussian process with L layers that converges to this stationary distribution in the total variation norm. Right. So there, we can show that in this case, the chain is ergodic and that you do converge to something. And so in that sense, there is a limit as the number of layers increases, right? So these are just some summary points. So let me just, because I know this talk is being recorded, so let me just quickly go through all of the references in case they're useful, and then I'll be very happy to take any questions. Thank you.
Thanks a lot. Thank you. Do we have any questions from the audience? If you put in the chat, we can allow you to talk to ask the question, or if you prefer to be in the chat. Right. So maybe I can ask the question. It's a more general question, I would say. So, I mean, in machine learning, deep learning, so I mean, one of the difficulty or challenges is sometimes these processes takes quite a lot of time. So how do you see whether the what you're doing here would it, how may it help in terms of possibility of maybe speeding up some of the process?
Yeah, so you mean the computational cost? Yeah,
yes,
the cost of actually generating these fields. Yeah. So you are right, it is a lot more expensive than standard Gaussian process regression. Yeah. So the value that I see in it is really if you don't have a lot of data. Right. So as usual with Bayesian inference, the prior is more important if you don't have a lot of data. Right. So here in the regression context, using these deep Gaussian processes is kind of using a better or more flexible prior. Right. So I mean, here for these things, I mean, if you do have a lot of data, then you're probably able to even constrain this one. With the standard Gaussian process, you're able to get quite close to the true function, but it would really need a lot of data and a lot more data than you would need with the deep constructions. No, but it is true. I mean, it's a lot more expensive than the standard GP. Yeah.
Any question from the audience or from the panel?
So Prudence, I don't know if you can see, but a couple of people have their hands up in the
oh, sorry. Thanks for letting me know. I was looking at the chat. Sorry. Right. So let me make people able to. So I didn't follow the order. Patrick.
Yeah,
Patrick O'Hara? Yes.
Can you hear me?
Yes.
Yeah.
We can.
Hi, I'm Patrick. I'm a PhD student from Warwick.
Mhm.
I had a question relating to the first talk we had today, which is, are there any Bayes bound results for deep Gaussian processes?
Sorry, I have to say I couldn't attend the first talk because of teaching, and I'm not that familiar with Bayes. So I'm not sure I can answer the question unless you can briefly say a bit more about what Bayes results are.
So it's probably approximately correct results. Perhaps I can look it up afterwards or send you a more specific question offline.
Okay, yeah, Patrick, Benjamin might be a better person to ask actually, because he probably knows what's been done for many kind of processes and models of learning with regard to Bayes. So, I mean, he might be a good person to drop a message to, I think.
That sounds good. Thanks.
Darren Wilkinson?
Hello. Yeah, can you hear me?
Yep.
Yes, yeah, we can.
Yeah, so I guess just a general question about deep GP constructions. So a natural thing to do might be to build a Gaussian process where, say, the length scale and the marginal variance are each determined by independent GPs. So that's not really like a 3-layer stack. That's sort of a second layer building onto previous layers. You know, have people studied sort of more general architectures for deep GP style constructions?
No, I'm not aware of anything in that direction. Yeah. So I think yeah, it just very quickly becomes a lot of different GPs, right? Because if you for each layer have 2 different ones. Yeah, no, I haven't seen anything in that direction.
Okay, thanks.
Thank you. I think there is a message in the chat as well. Is that Terry Lyons? Yeah. Would you like to
fine.
speak?
Thanks very much.
Yeah.
Thank you very much for your talk. I understand that this is, you know, really good stuff, and Gaussian processes are really a convenient way to learn things. But sometimes they really fall flat. And I think in my mind, it's for 2 reasons. One is that the data, the systems you're modeling, the functions don't even take all the values. For example, they lie on a circle, and the Gaussian is going to do its best to put points all over Rn. But perhaps more fundamentally, that they're really about, in my mind at least, and that's my question, about scalar valued functions. They're not very good at understanding and describing things which are vector valued, where the interactions are nonlinear between the different components. And I just wonder whether people are making progress and whether there are papers I should go away and read where they tackle these issues more or less head on. I mean, just to give a very simple example, I don't think it would work very well to simulate stereo sound, because the interaction between the 2 channels as somebody walks across the room is actually quite complicated.
Yeah. So I think emulating vector valued functions is still a bit of an open topic. So I mean, there are papers where I think you essentially try to learn what the covariance structure is from the data. But as you said, that's probably not going to work very well in most cases. So I mean, the only things that I'm aware of that kind of help with this a little bit is where you then specifically know what your function f is. So for example, if you know that your function f is the solution of a particular PDE, then, for example, there's a lot of recent work on incorporating PDE constraints, so things that you have a divergence-free function, or you have a monotone function, or your function satisfies a certain linear PDE. So there is a lot of work done in incorporating that sort of constraint. So I think that can then help with the correlation between different points, so incorporating that specific structure. There's also one paper that I'm aware of, which I guess is one very particular application where they again use that they know explicitly what the F is and what the different components of the outputs of F are, to define a proper covariance between all of the outputs in the Gaussian process prior. So it's done by FX Briol. I think he's now at Imperial. And I think also Mark Girolami is on the paper. I'm trying to remember what it was called. Sorry, I can't remember what it was called, but that's for a specific application, and I think in some computer vision. But again, you would have to use exactly that you know what your function F is and what the relationship is between the different outputs.
Okay, thank you. So, I mean, for example, if you had the data from a stream of patient measurements in a hospital ward, quite a good example of whether the simulations are going to work is, will it capture the fact that you have two blood pressures and one should always be bigger than the other? When real data often has lots and lots of complicated, vector value data had lots and lots of complicated non-linear constraints living in it.
Yeah. So yeah, if you're thinking of it just in terms of constraints, so having like a monotony increasing function and things like that, there is a bit of recent work recently. Yeah.
Great. Thank you very much.
Yeah. I mean, I'm sure you can find the references yourself, but I'm happy to, if you email me, I can send you some as well.
Thank you very, very much. Great. Thank you. Bye.
Thank you.